Welcome to your flipped classroom for lesson 6.4. Tonight we're going to look at exponential growth and decay functions. So what are some of the characteristics of exponential growth and exponential decay functions? Now there are two formulas that you need to know. The exponential growth formula, so I want you to grab a highlighter and I want you to highlight the exponential growth formula in your notes. And I want to look at it. I want to break it down. A is the initial amount. Now that could be an initial amount of money. It could be an initial population, initial amount of an item. But whatever the initial amount, that's either growing or decaying. That initial amount is going to go in place of A. R is the growth factor, which will always be the percent in your problem. And it's very important that you understand we're plugging it into the problem in decimal form. We can't just plug it in as a percent. We have to change it to decimal form. And then T is time, and I want you to add this to your notes. Understand time is going to be in years. Now I want you to highlight your exponential decay formula, and I want you to notice the one difference between the growth and the decay. Decay is y equals a times 1 minus r to the power of t. So again, A is that initial amount, R is the decay factor this time, which is still going to be the percent, and we're still going to change it into decimal form. And then T is our time. And once again, let's add the years. Okay, we want to make sure we understand time is supposed to be represented in years. Now, in example number 1, it says a website has 500,000. So right there is your initial amount. A website has 500,000 members in 2010, the number Y of members increases by 15%. So there's your initial amount, 500,000, and there is your growth rate. How do I know it's a growth rate? Because it says increases. So in example A, it wants us to write an exponential growth function that represents the website membership T years after 2010. So at this point, we're not actually going to solve for a final answer. We're just going to write the function. So let's start by writing the formula. If this is a growth problem, which according to our problem, the word increases by tells us it's a growth problem, we are using the formula y equals a times 1 plus r raised to the power of t. Now, if a is our initial amount, we know a website has initially 500,000 members. So we're replacing a with 500,000. And that's going to be times 1 plus. Now, our growth rate is 15%. So let's review, if we have a percent, how we can change it to a decimal. If I have a whole number, my decimal point is understood to be at the end, and I move that decimal 2 places to the left. That gives me the decimal form. So I'm plugging in a 0.15, and of course I don't know how much time has passed, so I'm leaving the t as a t. Now, one last thing to do, we're going to do all the work in parentheses that we can do. So 1 plus 1500ths is going to give me 1 and 1500ths, and then I'm raising it to the power of t. So there's my function. That's all I'm asked to do in A. I'm asked to write an exponential growth function that represents the website membership T years after 2010. Now, letter B says, how many members will there be in 2016? So I'm going to take this function that I wrote, and I'm going to bring it over here, remembering that it's 1 and 1500ths raised to the power of t. Now this time I can figure out, I know the initial membership was in 2010, and it's asking me how much the membership will be, or how many members there will be in 2016. So from 2010 to 2016, we know that 6 years have passed. So T is going to be 6. Now, if we follow our order of operations, please excuse my dear Aunt Sally, we know that we are supposed to do the exponent before we multiply. So in your calculator, you're going to take 1 and 1500ths, raise it to the 6th power, and then leaving that decimal in the calculator, we're going to multiply by 500,000. This will give me 1156530.383 3. Now, for our notes, we're going to put the whole decimal. Once we learn how to do this and we're taking quizzes and tests, we won't have to write the whole thing down. But it does tell us in the problem to round your answer to the nearest 10,000. Now notice it doesn't say thousandths, so we're not rounding to a point after the decimal point. They want us to round to the nearest thousand. So let's go back to elementary school for just a second. 0 is in the ones place, 3 is in the tens place, 5 is in the hundreds place, 6 is in the thousands place, and 5 is in the 10,000s place. So that's where they want us to round, which means I'm going to look at the number right here to the right, and since it is greater than 5, I know that my 5 is going to round up to a 6. Now, what happens to all the numbers behind the 6? They become zeros, including these numbers after the decimal point. But the question is, are the numbers after the decimal point, the zeros, are they necessary? And the answer to that would be no. So we can actually erase those last 3 zeros and that decimal point, and then just insert our commas. So after 6 years, the website will have 1,160,000 members. So as always, it's a word problem, so we are going to label it, but this is our final answer. Now, knowing the formula is going to be very important, so that's why I said I want you to highlight it in your notes. Now, let's step away from a word problem for a second, and let's look at a table. Can we determine whether the table represents an exponential growth function or an exponential decay function, or neither? Now, we learned in our lesson today that in order to figure out if this is exponential or linear, there's a small step that we have to do. So let's look at letter A. If we take the second term and we divide it by the first term, we can find a factor. So let's take our calculators, and if we do 16 divided by 64, we have 1/4. So we're going to see if by multiplying all the way across this table by 1/4, if we get all of these outcomes that are on the table. So take a minute, show that we're going to multiply from one term to the next all the way across the table, because it's got to work all the way across if it's going to be our problem. So let's see, we've got 64 times 1/4. If we put that in our calculator, we get 16. We multiply that by 1/4 and we get 4, which is the next value, and then we multiply one more time by 1/4 and we do get that last value of 1. So we know it's exponential. The question is it a growth or is it a decay? Well, we can look at the values and figure out 64 to 16 to 4 to 1. Our values are getting smaller. So this is exponential, and it is an exponential decay. So our final answer is exponential decay. The 1/4 is our work. The final answer is an exponential decay. And I'm sorry I had to squeeze that in there. It's not very pretty, but table A represents an exponential decay. All right, now let's look at letter B. All right, we're going to take 11 and we're going to divide by 4, because remember, if this is exponential, we're going to find a factor that we can multiply all the way across that will work. So if I do 11 divided by 4 on my calculator, I get the fraction 11/4. So we're going to multiply all the way across by 11/4, and I'm having to get creative here. We're going to see if 11 times 11 over 4 is going to get me 18. So I know that 4 times 11/4 will give me 11, but what happens when I do 11 times 11/4? Does that give me 18? And when I put that in my calculator, I actually get 121 over 4, which is a decimal of 30.25. So right here, I've discovered this is not exponential. This is a linear function. So in this problem, or it's possible that it's a linear function. What I do know is I'm asked to find if it's an exponential growth, exponential decay, or neither. So, since we know it's not exponential, we know it is neither, and that would be our final answer. Okay, but once again, we're putting into practice. We take that second term, divide it by that first term, and then we see if the factor we find will work all the way across the table. If it does, we know it's exponential, and then we just have to figure out if those values are getting larger or if they're getting smaller. Now, instead of looking at a table of information, we're going to look at an actual function, and we're going to determine whether the function represents exponential growth or exponential decay, and then we're going to identify the percent of change. Now, you'll notice this little note that I added right here is super important, okay? Here's how we're going to decide if it's a growth or if it's a decay. Is the number inside of the parentheses greater than 1 or less than 1? Because remember, in the formula, it's 1 plus r if it's a growth, it's 1 minus r if it's a decay. So, if the number in the parentheses is greater than 1, then we obviously have added a growth rate. If the number inside the parentheses is less than 1, then we have subtracted a decay rate. So that's why it's very important. We're going to look at the number inside of the parentheses, and it's going to tell us a lot. So if I go to letter A, I have y equals 2 times 92 hundredths raised to the power of t. So I am looking right now at this 0.92. Now, hopefully you can tell rather quickly that that number is less than 1. So we know pretty quickly that this represents an exponential decay. Because remember, if the number in the parentheses is less than 1, that means it is a decay. So that part is easy. Here's the part we gotta pay attention to. It also asks us to identify the percent rate of change. So what did they subtract from 1? And you'll notice the other little note I added is to find the difference between 1 and the number in parentheses. If you want to find the percent rate of change, we have to find the difference between that 1 and the number inside. So we're going to do 1 minus, because the difference of is subtraction, 1 minus 9.2, and we're just doing regular subtraction. 1's larger, so we're putting it first. 1 minus 0.92 or 92 hundredths gives me a decimal of 0.08. Now, this is a decimal, and we know it wants a percent. So, how do we change a decimal to a percent? We did this in class the other day. We moved that decimal 2 places to the right, and that makes our decay factor 8%. So we know it's decay because the number in the parentheses is smaller than 1. If we take 1 minus the 92 hundredths, we get 0.08. Move that decimal 2 places to the right, and it becomes 8%. Now, pause, see if you can figure out B. If I look at the number in the parentheses, 1.2, I know that the number is larger than 1. So rather quickly, I can tell that this is an exponential growth problem. The question is, what is the growth rate? So again, remember, we're going to find the difference between 1 and the number inside. Now this time 1.2 is larger, so we're putting it first. So 1.2 minus 1. If we do 1.2 minus 1 in our calculators, we would get 0.2. But that's a decimal. If we move that decimal 2 places to the right and we fill in that blank space with a 0, we find the growth rate is 20%. So that's how you determine if it is exponential growth or exponential decay, just simply by looking at the function. All right, now let's rewrite the function to determine whether it represents an exponential growth or an exponential decay problem. So we're going to go back to some lesson 6.1 properties. If you're looking at letter A, you have f of t equals 3 times 1 and 2 hundredths raised to the power of 10t. Now we know if they have multiplied a 10 and a t, then they have done the power of a power rule. So here's what we're going to do. We're going to bring down the problem exactly as it is until we get to this part of the problem. All right, we're going to move the 10 back inside the parentheses and put it with the 1 and 2 hundredths, and then that will leave just the unknown t on the outside. Now again, how did I know to move it back inside the parentheses? It's because they're multiplying 10 times t, and we know that the power of a power rule is the one that tells us to multiply the exponents. So we put that into our calculator, and we find out that we have f of t equals 3 times, if I'm going to round this to 2 decimal places, I have 1.218 on my calculator, so the 1 is going to round to a 2. I close the parentheses and I put the t. Now, I'm going to go back to example 3. What does the number inside the parentheses tell me? Well, if it is greater than 1, I know that this is an exponential growth problem. And I'm finished. So it's just a matter of knowing what to do with that exponent on the outside. All right, now let's look at letter B. And you're going to notice on your notes it says 0.05 on the inside. That is an error, so I need you to change that to 0.95 on the inside of the parentheses. Now let's look at the exponents, okay? They have t plus 2. So which rule tells us that we add the exponents? If we go back or we think back to 6.1, that is the product of a power rule. That's where we take two powers with the same base and we add the exponents. So we get to rewrite this problem as 0.95 raised to the power of 2 times 0.95, or 95 hundredths, raised to the power of t. Now let me go over that again, okay? Since they have t plus 2, we know, or we should know, that's the product of a power. That's multiplying two powers with the same base. That's how we know to add the exponents. So we're just rewriting it. We're giving each exponent the base of 0.95. Now, in our calculators, we can do 0.95 and we can square it, and we get a decimal. We want a decimal answer. We get the decimal of 0.90. So we're just going to leave it as 0.9. And then, of course, we can't do anything to the 95 hundredths raised to the power of t. So there is our rewritten function. Now, again, the inside of the parentheses tells us everything we need to know. Since 0.95 is less than 1, we know that this is an exponential decay. Okay? So the toughest part of this is going to be making sure we know how to rewrite the function, but that's going to require us to know our properties from lesson 6.1. Now I have one more problem for you, one more formula, compound interest. And if you look closely at it, okay, it resembles the exponential growth formula a lot, except we take the R, the growth percentage, we divide it by n, and we take the number of years and we multiply it by n. So what does n represent? Let's go look. P is the principal, the original amount. R is the annual interest rate. It's a percentage, and hopefully you've learned by now percents have to be turned into decimals before they go into these formulas. T is time in years, and then n is the number of times the interest is compounded per year. And they're going to tell us that in the word problem. So if we look at letter A, first thing we want to do is we want to write down the formula. So y equals P times 1 plus R divided by n, all raised to the power of nt. So let's read the problem. It says you deposit $500 into a savings account. There is my original amount of money. Times 1 plus, it earns 9% annual interest. So 9, if we want to change it to a decimal, move it 2 places back, it becomes 0.09 divided by. Now, the interest is compounded monthly. So if we're talking about a year, how many months are in a year? There are 12 months in a year. So if this interest is compounded monthly, it's compounded 12 times in 1 year. All right? Let me rewrite this. So that is 0.9 divided by 12. That also means it's 12 times, and it doesn't give us a year, so we're leaving it as a t. Now, the only thing left for us to do is do the work inside the parentheses. Can't do anything further than that because we don't actually have an amount of time that has passed. So we are just going to do that work inside of the parentheses. So 500 times. Now in the parentheses, we have to follow the order of operations. So I have to divide the 0.9 by 12 first, then I can add it to 1. And it gives me a decimal of 1.0075. Close the parentheses and raise it to the power of t. This is our final answer. We box it in, and we are done with lesson 6.4. Now tomorrow in class we're going to do a worksheet that is all about growth and decay functions, okay? Word problems where we're figuring out, is this a growth? Is this a decay? Which formula do we plug it in? And then working out the formulas. So make sure that you have highlighted those formulas, and I want you to go back to example number 2, and next to letter B, I want you to tell me one thing that you want to get for Christmas. I hope you guys have an awesome night, and I will see you tomorrow in class.